What Ming and Dan talked about was looking at problems outside of what we would consider the traditional area of computer science and trying to apply them to some classical problems that they're trying to solve inside the field of computer science. What I'd like to do with you today is give you a little sense of what it would be like to study computer science at the university level. We're going to work on an activity that is based on second-year university material and give you a foundation of some concepts that you would see in any university program, but in particular if you come here to the University of Waterloo. We're going to quickly talk about how data is represented, talk a little bit about what data or text compression is all about, and then we're going to do work on a particular activity based on a compression technique known as Huffman Coding. So every piece of data that is represented in a computer is represented with a binary code, a code that is made up of zeros and ones. And I'm sure you've seen that representation, or you've seen zeros and ones used to represent the idea of computer science all the time. So every piece of information, whether we're talking about genes represented within a computer science program context or rap lyrics, text, pictures, sound, anything that you can think of that is showing up on a digital device has a 0 and 1 code associated with it, known as its binary code. And normally what we do is we group those bits, those zeros and ones together into groups of 8, and we call that a byte. And a byte is a standard unit of measurement for space in memory. Simple text, normally, if we talk about just English-based text, can normally be represented by a single byte of information. But we've actually expanded how we talk about, or the kinds of data that we're going to talk about. And we include things like, if we want to be able to represent all the characters in the Chinese alphabet, all the emoticons that we would include in an email and things like that, all those kinds of characters, we actually need 2 bytes together to represent all the different combinations to assign codes to any particular character that we might see there. So the standard size for representing a single character in a text document would be 16 bits worth of space. What we want to talk about when we talk about data compression is how do we take that standard size, 16 bits per character, and reduce it to a smaller amount. And there's lots of techniques that we can use to do that. And I want to get you to one of them. I know we're running a little short on time here. There are some very standard techniques that we see, and the techniques differ depending on what the original data source is. So I'm sure you've heard of Jpeg files. Jpeg is a standard way of compressing digital images. And it's a different technique than what we would use for compressing something like sound. And a standard technique for compressing sound files would be an MP3. So that's what those file extensions mean. They are compression techniques. Standard way of compressing text is known as zip. I'm sure you've done this yourself. You zip files together. And that technique is actually based on an algorithm called Lempel-Ziv, which uses patterns within the text. That's not the technique that we're going to use here. One thing you want to think about when you're talking about compression techniques, generally speaking, is whether they are lossless techniques or they are lossy techniques. So a lossless technique says I'm going to take data and I'm going to compress it, and I'm going to send it off, and somebody's going to receive that data and then decompress it, and the result that they get on the other end is going to be exactly the same as what we started with. That's a lossless technique. And that's something that we would use. That's the technique we would rely on if we were talking about text data, or certainly DNA information. These are very precise pieces of information that we want to have a guarantee that what we get out from our compression is exactly what went into the compression. But there are also lossy techniques that we can take advantage that would be potentially faster or more effective techniques. And those can be used on media such as sound or video or images, because we wouldn't necessarily notice a few pixel deviations in a picture that has been compressed and decompressed. And if we want to do things like have streaming video and streaming audio, it's more important for us to have the speed of the information being sent to us rather than the exact tonal quality or video quality of what we're seeing. We can fill in the blanks as human beings. But we're going to talk about a lossless technique called Huffman Coding. So how does Huffman Coding work? As I said, a standard length for every bit of information, every character that we would want to have in a text would be 16 bits. Now, we could reduce that size very, very easily by recognizing how many bits we would need to compress a particular piece of text. So if I have a book written in English, for example, I'm not going to need 16 bits to represent all the different characters that I might see in that book, right? So first of all, let me ask you, if I was to hand you an English language book, what is the character you expect to see most often in that text? E? Any other guesses? T? Any other guesses? A, S? Haven't heard it yet? Space. Space, exactly. Right? You're going to have a space probably about every 5 or 6 characters. So don't forget we have to represent all the spaces, all the punctuation, all the quotation marks, everything that is going to appear in that book. But basically we're going to have 26 letters in the English language. We have to have a different representation for uppercase letters as lowercase letters. We're going to need representations for spaces and question marks and so on. And we could probably do that with we certainly can do it with less than 16 bits. We might be able to do it with less than even 8 bits, depending on what the total number of different characters we have to represent. So how many bits, we have to decide, how many bits is it going to take us to represent a certain number of different characters? Well, if I have 1 bit, I have 2 different codes I could use, either 0 or 1. If I have 2 bits, there's 4 different characters, 4 different codes I could use. I could use 00, 01, 10, and 11. If I have 3 bits, how many different codes could I come up with 3 bits? 8. If I have 4 bits, how many codes could I come up with over 4 bits? 16. Then 5 bits would be 32, 6 bits would be 64, and so on. So I have to decide how many different characters. And I might be able to do it in an English language text with just 64 different codes. So I might only need 6 bits to handle that. Rather than using the same length code for every single character in our text, what Huffman Coding says is what I'm going to do is I'm going to use a variable length code. And I'm going to recognize that things like space and E and S and T appear more often in an English language text than things like X and question mark and semicolon. And so I'm going to use really short codes for the characters that appear most often, and I'm going to use really long codes for the characters that appear less often. And when I combine that, I'm going to end up with a binary coded version of the text that is shorter in total. Because if I have 2-bit codes for things like E, and E shows up all the time, and if I have a 12-bit code for something like semicolon, semicolon only shows up every once in a while, overall I'm going to end up with less bits in total. The trick here is, though, when I have a standard length coding of something, I know exactly when I have reached the end of an encoding of a particular character. So if I'm reading something in binary and I know the standard length for the code is 8 bits long, say, what I'll do is I'll read 8 bits, I'll look up on a table to see what that code represents in terms of the English language letter, and I'll convert it. And then I'll read the next 8 bits and I'll convert it. And then I'll read the next 8 bits and so on. If I have variable length codes, I don't know up front how many bits it's going to take me before I reach the end of a particular character. So I need some way of figuring out when I have reached the end, when I have read all the bits that represent a particular character. And I have to create something called a prefix-free encoding. And I do that using something called a binary tree. And this is a standard way of representing information. It's something that you'll learn even in first-year computer science here. Certainly you would learn it in second-year computer science. So a binary tree is upside down compared to what we would think of as a regular tree, because a binary tree has its root at the top. It has nodes that contain information. In this case, they're containing numbers. The end nodes are known as leaf nodes. They don't have anything leading from them. There's links between the nodes called branches. A tree has it's a recursive structure. So a branch of a tree leads to what's known as a subtree, which has all the properties of the main tree. And the data is stored, as I say, inside the nodes of the tree. This particular tree is a representation of encoding for a particular message using Huffman coding technique. And the encoding comes from reading the path that leads you from the branch, from the root of the tree to a leaf node. So if I wanted to figure out what the encoding for a particular letter is, like the B, for example, what I do is I take a walk from the root of the tree to the B, and every time I move to the left, I record that as a 0, and every time I move to the right, I record that as a 1. So from the root of the tree, ignoring the numbers, don't worry about the numbers here, I'm going to move left, which is a 0, then right, then right, then right again, and then to the left. So the Huffman code for a B from this tree would be 0, 1, 1, 1, 0. That's a 5-bit code. What I would like you to do is you have in your packages a sheet. Unfortunately, it's front to back. So I'm going to have you work in groups so that you can have one person have the tree showing and the other person can record your information on the chart. Using that information, what I would like you to do is I'd like you to figure out the encoding for each of the characters in this particular message. And there are 12 characters, I believe. So there's E. The second one there from the left is a space. It's hard to represent a space on typed paper. Then an L, an A, a B, a Y, an S, a T, an R, an O, and an H. So for each of those characters in a message, figure out what the Huffman coding is based on this tree. Don't worry about where it says frequency. I'm not worried about that now. I'll give you a few minutes to do that. Okay, one thing I'm just going to bring you back together here for a minute. One thing I want to emphasize here is that the codes that you are generating for these characters are prefix-free codes, which means that the code for one of the characters is not the beginning of the code of another character. And that's essential for variable length encoding. Because if I said, I just randomly picked a code for E, and I said E is going to be 0, 1. And then I'm going to pick a code for S, and I'm going to say that's 0, 1, 1. If I don't know how long the code is, and I start reading a 0 and then a 1, I don't know if that's the code for E or if that's the beginning of the code for S. So it's essential with variable length encoding, I have something like a binary tree to help me generate prefix-free codes. And what it is about the binary tree that does that is, if I think about the path I have to take to any letter, it is not the beginning of the path for another letter, because all the letters are appearing within the leaves of this tree. So the code for H cannot possibly be the beginning of the code for anything else, because that's the end of the path in this tree. We don't have a ton of time here. So the second part of the activity is to take an encoding, a series of bits, and figure out what the message is. The easiest way to do that is to use the tree. So what you do is you start reading off the bits in your message. I don't have the message up on my slides here. But you read the message, you start at the top of the tree. If the bit is a 0, you go to the left. If the bit is a 1, you go to the right. And you keep on following a path, following bit by bit, until you reach a leaf. Then you record the letter that goes along with that, and mark where you were in the message. And then start back at the root again. So go through and see what you can do to decode the message that is in that whole 0s and 1s. And you might get partway through it and figure it out before you get to the end. Okay, I'm going to pull you back one more time. I know at least a few people got the message. What is the message? Yeah, she sells seashells by the seashore. This is an unusual message because the most often used character in that is S. And if you look at the code for S, it is very short, right? It's just two bits long. And the characters that appear least often, like Y and R and O, they have codes that are quite long. I'll just give you a few other things to think about before you leave, and that is the numbers that you see in this tree are frequencies. So if you were to count the number of times that characters appear within the tree, or within the message, you'll see those as values in the numbers of the nodes of the tree. And that there would be a different tree that you would create for every different message, because it depends, this particular technique is going to depend on the actual frequencies of characters, and S isn't going to be the one that appears most often in most messages. I hope you had a great day. Sorry we were cut off a little bit here today. Enjoy the rest of your time.